Hello and welcome back. In the previous few videos, we've discussed the forces that are exerted with magnetic fields. However, we haven't really talked about where these magnetic fields come from. So the origin of magnetic fields was first discovered in 1820 by a man named Hans Christian Ørsted, who noticed that current-carrying wires will deflect the needle of a compass, and Ørsted quickly realized that this meant that a current-carrying wire actually generates a magnetic field. So what exactly do these magnetic fields look like? Well, if you have a long, straight, current-carrying wire, the magnetic field lines form concentric circles around this wire. And the direction of these magnetic fields can be found using another right-hand rule. So, to find the direction of the magnetic field, you take your right hand and you point the thumb on your right hand in the direction that the current flows. And when you do this, the rest of the fingers in your hand will curl in the direction of the magnetic field. So, for example, in this figure here, we have current that's flowing out of the screen. So if I orient my right hand so that my thumb points directly away from the screen, then I can see that the fingers on my right hand are going to curl in this counterclockwise direction. Now this gives us the direction of the magnetic field, but how do we calculate the magnitude of the magnetic field? Well, that's given by this equation right here. So the strength of the magnetic field is equal to mu naught I divided by 2 pi r, where this number, mu naught, is called the permeability of free space, and is equal to 4 pi times 10 to the minus 7 Tesla meters over amps. I is the current carried through the wire, and r is, of course, the distance between the point where you're calculating the magnetic field and the wire. So let's take a look at an example. In this example, we have 3 current-carrying wires, and each of these wires are placed at the corner of a square like I have shown in this figure down here. And I'm told that the current flowing through wire 1 is equal to the current flowing through wire 2. And the question is how much current must be flowing through wire 3 so that the total magnetic field up here at this empty corner of the square is equal to 0. Now, one of the things that I'd like to point out about this is that the directions of these magnetic fields are just right so that they can cancel at this empty corner. So for example, here, wire 1, if I calculate the direction of the magnetic field created by wire 1, well, remember, the way we do this is that we point our thumb in the direction that the current is flowing. So here, this X indicates that the current is flowing into the screen. So when I do that, I see that the magnetic field generated by wire 1 tends to point in this clockwise direction. So this is my magnetic field generated by wire 1. And I can see that the magnetic field generated by wire 1 at the top right corner points straight down. So these are my magnetic field lines. Now looking at wire 2, down here, again, this current is also pointing into the screen. So the magnetic field lines for these are also going to point in this clockwise fashion. So we're going to have these magnetic field lines that are going to kind of point like this. So that means that up here at this top corner, my magnetic fields are going to point towards the right. So here we have magnetic field lines that are pointing down. Here we have magnetic lines that are pointing towards the right. So if I add the magnetic fields created by wire 1 with the magnetic field that are created by wire 2, I'm going to have magnetic field lines that are pointing down and towards the right, Because I have magnetic field lines that are pointing down caused by wire 1, so this is B1. I have magnetic fields that are pointing towards the right caused by wire 2, and so the sum of these things points down and towards the right. And looking at wire 3, now wire 3, the current is flowing out of the screen. Now if I orient my right hand so that my thumb points away from the screen, now I can see the fingers on my hand are going to point counterclockwise. So my magnetic field created by this wire is going to point counterclockwise. So this means that up here at this top corner, my magnetic field is going to point up and towards the left. So here we have this third magnetic field that's pointing up and towards the left. And this is the magnetic field created by wire 3. So we can see that these magnetic fields are in fact perfectly oriented so that they can cancel out. Now I'm going to need some room to actually work through this, so let me go ahead and open up a blank screen. So here I have drawn on the left another picture of this problem, and remember the idea is that the magnetic field up here has to be equal to 0 Tesla, And then over here on the right, I'm just showing you a vector diagram of what's going on. So the magnetic field created by wire 1 is pointing down, the magnetic field created by wire 2 points towards the right, and the magnetic field created by wire 3 points up and towards the left. Now, the important thing to understand about this is that if I add together the magnetic fields created by wire 1 and wire 2, this is going to point perfectly down and towards the right. So let me draw that here. This is the magnetic field of wire 1 plus the magnetic field of wire 2. And since this points in the opposite direction as the magnetic field created by wire 1, the magnetic field created by wire 3, if the magnitude of the sum of these two vectors is equal to the magnitude of the magnetic field created by wire 3, then these two things will perfectly cancel out. So right away, I can say that the magnitude of the net magnetic field created by wires 1 and wire 2 is equal to the magnitude of the magnetic field created by wire 3, then the magnetic field at the empty corner will equal 0. Now, what is the magnitude of the sum of these two magnetic fields? Now, let me go ahead and just label this box. Let me call this distance right here r. So that's the length of one side of the square. Then the magnitude of either of these two magnetic fields is going to be equal to mu naught I divided by 2 pi r. And this magnitude is going to be the same for these two wires because they're both the same distance away from the empty corner and they both have the same current flowing through them. So how do we actually calculate the magnitude of the sum of the two magnetic fields if they both have a magnitude of mu naught I divided by 2 pi r? Well, let me go ahead and draw the actual vector diagram for the sum. So remember, to do this, we place the vectors head to tail. So here we have the magnetic field created by wire 1, which points down. The magnetic field created by wire 2 points towards the right. And the sum of these two points down and to the right like this by connecting from the start of the two vectors to the end of the two vectors when we place them head to tail. So this is the sum of the magnetic field created by wire 1 plus the magnetic field created by wire 2. And so hopefully you can see that because this forms a right triangle, that the magnitude of this sum, so this is going to be the magnitude of b1 plus b2, we can just use the Pythagorean theorem to find this length. So it's going to be equal to the length of b1 squared plus the length of b2 squared, and all of that's going to be square rooted. But of course, the magnitude of either one of these two magnetic fields is the same. It's just equal to mu naught I divided by 2 pi r. So if we plug this in, we'll have mu naught I divided by 2 pi r squared plus mu naught I divided by 2 pi r squared. And we're going to add those two together and square root it. So that's just going to be equal to the square root of 2 times mu naught I divided by 2 pi r. So that's the strength of the total magnetic field created by wires 1 and wires 2, so the sum of those two magnetic fields. And that has to be equal to the strength of the magnetic field created by wire 3. So we can say that the magnitude of the magnetic field created by wire 3 has to be equal to square root of 2 times mu naught I divided by 2 pi r, where this I is the current flowing through wires 1 and wires 2. Now, what's the formula for the magnitude of the magnetic field created by wire 3? Well, we have to be a little bit careful about this. So this is going to be equal to mu naught times the current flowing through wire 3 divided by 2 pi, and in this case, the distance between wire 3 and the empty corner is no longer equal to r. So hopefully you can see that because this distance is r and this distance is r, by the same type of Pythagorean theorem, this total distance from this corner all the way up to this corner is going to be equal to the square root of 2 times r. It's exactly the same type of thing we had here when we added up these two vectors. So this total distance is the square root of 2 times r. So now if I try to solve for this current, well, I can see that the mu naughts cancel, the 2 pi's cancel, the r in the denominator cancels, so I have I3 divided by the square root of 2 is equal to the square root of 2 times the current flowing through wires 1 and wires 2. So that means the current flowing through wire 2 is going to be equal to 2 times I. Or I'm sorry, the current flowing through wire 3 is 2 times I. So, in the end of the day, the current flowing through wire 3 was just twice the current flowing through either wires 1 or wires 2. But the interesting thing about that is that you might have guessed that at the beginning because you said, well, I've got one wire, it's trying to cancel the magnetic field created by 2 wires, so I have to have twice the magnetic field. But it's actually quite a bit more complicated than that because these magnetic fields were pointing in different directions, so that only gave us a factor of square root of 2, but then we gained another square root of 2 because this wire 3 was further away from that empty corner. So let's go ahead and look at another example. So the second example says we have a 6 microcoulomb charge which is moving at a speed of 7.5 times 10 to the 4 meters per second in a direction that's parallel to a very long straight wire. The charge is 5 centimeters from the wire, and the wire carries a current of 67 amps in the direction that's opposite the direction that the charge is moving. The question asks us to find the direction and magnitude of the force that's exerted on this charged particle. So the idea behind this problem is that this current-carrying wire is going to generate a magnetic field, and this magnetic field is then going to exert a force on this moving charge. So to find the direction of the magnetic force, the first thing we need to do is determine the direction of the magnetic field created by this current-carrying wire. And remember, the way we do this is by applying the right-hand rule. So you first point your thumb in the direction that the current is flowing. So here in this picture, the current is flowing into the screen. So if I orient my right hand so that my thumb points into the screen, I can see that the fingers on my right hand are going to curl around in a clockwise direction. So that means that my magnetic fields are going to kind of look like this. And that means that where this charge is, my magnetic field lines are going to point vertically upwards. Now the second part is we need to find the direction of the magnetic force exerted on this charge. And to do that, we have to apply another right-hand rule. So the first thing you do is you point your fingers in the direction that the charge is moving. So here I tell you that the charge is moving away from the screen or out of the screen. So if you orient your hand so that your fingers point away from the screen, and then rotate your hand so that when you curl your fingers will point towards the top of the screen where the magnetic field is pointing, then your thumb should point towards the left. So that means the magnetic force exerted on this charge points towards the left. So now how do we calculate the magnitude of this force? Well, remember, the force exerted on a charged particle is given by this formula here. It's QVB times sine of the angle between the velocity and the magnetic field. Now if we go back here, we can see that the velocity is pointing perpendicular to the screen, but the magnetic field is pointing vertically upwards. So that angle, theta, the angle between the velocity and the magnetic field, is 90 degrees. And sine of 90 degrees is just 1. So this is just going to be QVB. Now the second part is that we have to find the strength of the magnetic field. And of course we found the formula for that earlier in this video. That's mu naught I divided by 2 pi r. So if I plug that in for the magnetic field, then the force is going to be that times Q times V. And since I've been given all these values, because I know the current flowing through the wire, the distance is 5 centimeters, the charge is, I didn't give you that. Oh no, I'm sorry, it's 6 microcoulombs, and the velocity is 7.5 times 10 to the 4 meters per second. If I plug all this into a calculator, I can see that the magnetic force is going to be equal to 1.2 times 10 to the minus 4 newtons. So that's the force that's exerted on this charged particle, which is moving parallel to this current-carrying wire. Now, the next thing that I want to look at is the magnetic force that is exerted between current-carrying wires. And the basic idea is that because current-carrying wires generate magnetic fields, and because magnetic fields exert forces on current-carrying wires, if I have two current-carrying wires, they'll actually exert a magnetic field on each other. So what exactly does this force look like? Well, let's go ahead and calculate the direction of the force exerted on this wire on the left. So to do that, I first need to find the direction of the magnetic field created by the wire on the right. And remember, to do this, we apply the right-hand rule. So you need to point your thumb on your right hand in the direction that the current flows, and then your fingers will curl in the direction of the magnetic field. So here we have an X that indicates that the current is pointing into the screen, and if I orient my thumb on my right hand so that it points into the screen, I can see my fingers are going to curl in a clockwise direction. So my magnetic field looks a little bit something like this. And that means that at this point right here, where this wire is, my magnetic field points vertically upwards. Now, if I apply the right-hand rule again to this wire, I can find the direction of the force. Now remember, to do this, you first point your fingers in the direction that the current is flowing. So here we have a red dot that indicates that the current is flowing out of the screen. So if I orient my hand so that my fingers point away from the screen, and then I rotate my hand so that when I curl the fingers on my right hand, they're going to point towards the top of the screen, then I can see my thumb is going to point towards the left side of the screen. So here, what I can see is that the magnetic force that's exerted between these two wires is actually going to be a repulsive force. So this wire is going to exert a magnetic force which points towards the left, and this wire is going to exert a magnetic force on this wire that's going to point towards the right. And it turns out that anytime you have wires that are carrying current in the opposite direction, there will be a repulsive force between them. And anytime you have wires that carry current in the same direction, there will be an attractive force between them. And if you have a hard time remembering this, the way I always think about this is that if I had a single current carrying wire, so here I've got a wire and let's say it's carrying current into the screen, I could always imagine breaking this wire up into two parts. And then the right half of this wire will have to exert a force on the left half of the wire. And if this was a repulsive force, then anytime you carry current through a wire, these magnetic forces would just tear the wire apart, especially if you had something like stranded wire. But of course, what happens in real life is that when you carry current through a wire, the wire is actually pulled together. And that's because it's an attractive force between wires that are carrying current in the same direction. So let's take a look at a very simple conceptual example. And in this example, we have a long current-carrying wire that's placed next to a current-carrying loop. And the question I want to ask is, what is the direction of the magnetic force exerted on this current-carrying loop? And you may want to take some notes on this because I'm actually going to ask you to calculate the total force exerted on this loop in the problem set. So the basic idea is that up here we have this current-carrying wire, which is flowing towards the right. And on the top part of this loop, I have a wire where the current is also flowing towards the right. And remember that the magnetic force between wires where the current is flowing in the same direction is an attractive force. So the magnetic force exerted on the top part of this loop points upwards. Now, conversely, on the bottom part of the loop, there is current that's flowing towards the left. So we have here current that's flowing towards the right on the top and current that's flowing towards the left on the bottom. So these two currents are pointing in the opposite direction, and remember that the magnetic field exerted between wires carrying current in the opposite direction is a repulsive force. So here we have a magnetic field that's going to point, a magnetic force, which is going to point downwards. So now the direction of the net force acting on this loop is going to depend on which of these two forces is greater. Now we found on the previous slide that the magnetic force exerted on a wire is equal to mu naught I1 I2 L divided by 2 pi r, at least when the wires are parallel, so we don't have to worry about that sine theta term. So here we can see that this magnetic force decreases as this distance gets larger. So what that means is the magnetic force exerted on the top part of this loop is going to be larger than the magnetic force exerted on the bottom part of this loop because the top part of the loop is closer to this current carrying wire. So that distance r will be smaller for this top part than it is for the bottom part of the loop. So let's go ahead and take a look at one more example. In this example, we're told that two long straight wires are hung from the ceiling. The wires have a mass per unit length of 0.05 kilograms per meter. The string that the wires hang from are 1.2 meters long. So when identical currents flow through the wires in opposite directions, the wires are going to repel, and they're going to form a 15-degree angle between the two wires. The question asks us to determine the current that's flowing through the two wires. So here I have a picture kind of showing you the idea. So we have these two wires. They're hung from the same point by strings that are both 1.2 meters long. And on the ends of these strings are current-carrying wires that are carrying current in the opposite direction. So they're going to exert a magnetic force that's repulsive between the two of them. And this repulsive force is going to cause them to form this 15-degree angle between them. And the question is that if this angle is 15 degrees, then what's the current that's flowing through these two wires? So once again, I've drawn a picture of the problem that we're looking at. And in order to see how all these forces are related, let's go ahead and start by drawing a free body diagram of this wire right here. So there are three forces that are acting on this wire. There is the gravitational force, which pulls down on the wire. There is this magnetic force. Remember, it's a repulsive force, so it's going to point towards the right. And then we also have the tension of the string, which is pointing up and towards the left. And if this wire is in equilibrium, then the sum of these three forces has to equal 0. So that means that if I place these vectors head to tail, they have to go back to where they started. So here we have the gravitational force, we have the magnetic force, and then the tension force. And so this whole thing has to form this closed triangle like I have shown here. And this angle right here, that's equal to 1/2 of this 15-degree angle. So if I kind of like bisect this, hopefully you can see that. Right? This is the direction that my gravitational force is pulling. It's pushing down. My tension is pulling up like this. This angle is going to be half of 15 degrees, so it's going to be 7.5 degrees. So that's this angle right here in my force diagram. So looking at this triangle, we can see that what I want to do is I want to relate this magnetic force, so I can solve for the current, to this gravitational force. So I can relate these two sides of the triangle using tangent. So remember, tangent is opposite over adjacent. So we have tangent of the 7.5 degrees is going to be equal to, so opposite this angle is the magnetic force, and adjacent to this angle is the gravitational force. Now, the magnetic force exerted between two wires, remember that's equal to mu naught I1, I2. In this case, we're assuming the wires carry the same current, so that's just going to be I squared times the length of the wire divided by 2 pi r. And we're going to divide that by the gravitational force, which is mg. So right away, we can see that this magnetic force is going to depend on the distance between the two wires. So how do we calculate that? Well, let me go ahead and draw another picture of the problem. So here we have these two wires, and there's this angle of 15 degrees between the two of them. And what I want to do is I want to calculate this distance right here. And the way I'm going to do this is by bisecting this so I create a right triangle. And I want to consider just half of this. So this is going to be 1/2 of r. And remember, these strings have a length of 1.2 meters. So right away, I can see that we have this triangle that we're forming right here. So this length right here is r/2, or 1/2 r. This length right here is going to be 1.2 meters. So I can calculate this by using the sine of the angle 7.5 degrees. So if I look at this, triangle right here, actually let me go ahead and just redraw this triangle. So this side right here is r/2. This is 1.2 meters, and this angle is 7.5 degrees. So you can see that sine of 7.5 degrees is going to equal r/2 divided by 1.2 meters. So that means that r is going to be equal to 2 times 1.2 meters times sine of 7.5 degrees. So now we can plug that into this formula for the the magnetic force. So we have tangent of 7.5 degrees is going to be equal to, so this is going to be mu naught I squared L divided by 2 pi mg, and r, remember that's equal to 2 times 2.1 meters. Actually, let me get rid of that multiplication sign. So it's 2 times 2.1 meters times sine of 7.5 degrees. And so now what I need to do is I need to solve for the current. So if I just rearrange this to solve for the current, I can see that I squared is going to be equal to, so this is 2 pi mg, 2 times 2.1 meters. Actually, let me go ahead and combine these two 2's. So this is 4 times sine of 7.5 degrees divided by, times tangent of 7.5 degrees divided by mu naught L. So now if I just square root both sides, I have the current is going to be equal to the square root of this. And if we just consider 1 meter of wire, so we know the mass of 1 meter of wire, so I can plug in 1 meter here. The mass of 1 meter of wire, remember, I think that's 0.05 kilograms. So we have 0.05 kilograms here. G is 9.8. We can calculate sine of 7.5 degrees. We can calculate tangent of 7.5 degrees. So we can plug all this into a calculator, again just using that L is equal to 1 meter and that the mass is going to be equal to 0.05 kilograms. So if I plug both of those values into this formula, I can see that the current is going to equal 318 amps. So you need a very strong amount of current flowing through the wires in order to just deflect them by this very small amount of 15 degrees. So hopefully that gives you just some kind of idea of how small these magnetic forces really are when we compare them to the typical type of forces that we deal with, like the gravitational force. And so I think I'd like to end the discussion on the origins of magnetic fields with this very long and disgusting, it's ugly-looking example. And in the next video, I'm going to talk about something called electromagnetic induction, which is how changing magnetic fields can actually create electric fields, and that's how we generate electricity inside a power plant.